And what I'm going to do is to talk a little bit about rocket science. And you could say, rocket science, why about that? Yeah, the perspective of rocket science. Rocket science or space research is really interesting because it gives us literally a new perspective on the world we are living in. Because we get a vantage point that is completely different to the vantage point we have normally. Normally, we live on Earth. Most of us do. Few get the chance to get into space. But most live here on Earth, and we look down. We tend to look down. We rarely look up. We should do it a little bit more often. But when we are in space, then we can look down, and we can see things that we otherwise can't see. And now it would be nice to have the slides in order to... oh yeah, thank you very much. So yeah, rocket science, as I said, and it gives us the opportunity to give a completely different perspective on our world. And this can literally change our state of mind. And some people, they actually think that it has done. An example, yes, I will take you back more than 50 years. It was in December 1968. For the first time, humans left Earth and they were orbiting the moon. They were orbiting the moon. It was the crew of Apollo 8. And they, orbiting the moon, were able to see this with their eyes. And they were able to take this photograph. The NASA astronaut William Anders took this image that has become iconic in our perception of the world. It is called Earthrise. Because when you are in orbit on the moon, around the moon, you are able to see the Earth rise over the moon's horizon. And this image here, it had a profound effect. Because when you look at this image, you see our planet, Earth, as this beautiful, blue, fragile marble on a backdrop of a black universe and in stark contrast to a gray, unfriendly lunar surface. It really tells you that the place we are living is special and you should really do what you can to preserve it. Many people argue that this image actually was the onset of what you can call the environmental movement. The onset of a higher degree of responsibility, a recognition that we cannot just exploit nature's resources and throw our waste back in her face, that we really have to think about what we are doing. So one single photo taken from a space mission can really change a lot. But space research is not just about taking photographs. It's about obtaining a lot of data. And you could say that many of the results that form the basis of modern climate research, they are based on space data. They are based on satellite observations, as Bjørn already mentioned, that for many, many years have observed, for example, the Arctic, but also the entire globe, providing key data points for us to investigate and to create our models for how the climate is evolving. Sometimes data can be very difficult to handle. I mean, climate research, it is presented in scientific magazines, journals. It's highly technical. There are a lot of data. There are a lot of numbers. There are a lot of plots. But it can be very hard to digest if you're not studying it on a daily basis. But there are ways around that. What you see here looks like a kind of an artistic version of the French flag, the tricolore, the bleu, blanc, rouge. But it's actually a new way of looking at climate change. Ed Hawkins, who is a climate researcher at the University of Reading, he has made a simple way of visualizing the temperature of Earth. So he has taken climate data, average temperatures for each year for the entire globe, and then he has calculated the average, and then when you see a blue color, it's below the average. If it's a red color, it's above the average. This is for the entire globe from 1850 until the year 2018, our last year. And you can see it starts below, then it gets towards the average, and the most recent years it has only been doing one thing, going steeply up. So this is a way of kind of visualizing these data in a way that everybody should be able to comprehend. And you can go to his website, showyourstripes.info, and you can get a plot for your region of the world and see how things have been evolving. As I said, scientific data give us an insight. Bjørn talked about the melting glaciers, and here you see an example of one of the most well-studied glaciers in the world. It is the Jakobshavn Glacier at the city of Ilulissat in Greenland, on the west coast of Greenland. And not so many years ago, this glacier was actually stretching all the way out to the ocean. But as you can see now, the glacier now has receded because it is melting at an ever-increasing pace. Images like that, this is taken on the 29th of April this year by the European Copernicus program, is supplemented by other kinds of measurements. This is a radar satellite. It's the European Cryosat-2 satellite. And for many years, it's been doing radar measurements of the ice, so we can measure the height of the ice, but you can also measure the changes. And that's something that's very important when you want to study a system, for example, the climate. You want to study how things are, but more importantly, you want to study how they evolve. So you want to get data over long time spans so you can see how things were and how things are now. And from these trends, you're able to say something about the dynamics, how things are changing. So from the data made by the Cryosat satellite, some of my colleagues at our institute and international collaborators have made this map where you can actually see the height changes, and the red spots here are actually places where you have glaciers. Here's the Jakobshavn Glacier at Ilulissat, which you saw on the photo before. And these are the velocities, and you can see there's really a lot happening here. So melting is increasing, and when you have these data, then you can start using them to put them into models. And I'm not talking about Lego models, because we're not allowed to do brand placing. So we are in a situation where we can take these things and put them into mathematical models and say, okay, this is the situation now, and with the knowledge we have about the physics and the things that are going on, how are things going to evolve? In order to get more detailed information, we are actually not just using satellite data. Sometimes, in order to do the models in a better way, you need to go closer. And you can do that in many ways. You can step onto the ice, as Bjørn was telling. That's also very important as to ground truth the satellite data, to know what is it exactly the satellite is looking on. There's only one way to find out, is to go and have a look at it. But there's also an intermediate possibility, and that's the use of unmanned systems or drones. This is a drone flown by our institute. It's over the ice just off the city of Kangerlussuaq in Greenland. And the reason for me actually being here in South Korea this week is because we are initiating a collaborative project together with the Korean Aerospace Research Institute and the Korean Polar Research Institute to employ drones developed here in Korea by KARI to use them to study the glaciers in Greenland. To get more detailed information, better, sharper pictures, and drones also have this advantage that they are more flexible. Satellites are in specific orbits. You cannot just move them around and say, hey, go back and look again. You can do that with a drone. So you have to have a layered approach to your research. Satellites give the big picture and a continuous picture. Drones can get the details, and you also need boots on the ground, so to say, in order to validate everything you're observing. That's hard work, but it's very important, because without the data, we cannot do the models, and there we cannot say anything qualified about how and where we are going. And as already mentioned by Bjørn, the ice is melting. The sea ice is not as such a problem. It has consequences, but it doesn't add to sea level rise because there's already a balance. It's like when you have ice cubes in your drink. Even if they melt, the glass will not overflow, or maybe it's just because you're drinking your drink, but that's another issue. But the ice sheets, Greenland ice sheet and Antarctica, that's a different story. And this is a research result that just came out last week by Andy Ashwanden and colleagues from my institute in between, who have looked at 3 different scenarios for the world, starting today with the situation as it is now, where you can see how the ice is flowing off from the glaciers. And this is a low emission model, so if you reduce the emissions of greenhouse gases significantly, this is a medium scenario, and this is a scenario with high emission, which is pretty much where we are today. And this scenario here, especially the extreme one, it says that in 1,000 years, the ice sheet in Greenland will be melted completely. This will result in a 7.3 meter sea level rise. And this is only Greenland. This is not looking at Antarctica. And this is based on today's situation combined with the physical knowledge and, of course, the assumption of, so this you could say, which one should we pick? Should we just let things stay as they are? Then we will end there and you say, 1,000 years, does it really matter? No, but already in a few years, in 100 years, we will have significant sea level rise because of this, as Bjørn already stated. Now, it shouldn't be a doomsday talk, this, and we of course have to talk about where do we go, what do we do? Well, I mean, it seems obvious that we should limit greenhouse gas emissions, but the problem with that is to find a viable substitute. And the problem here is that we have a huge population on Earth. We are going fast towards 8 billion people, and it has to be solutions that are sustainable in order to these people can have a decent and reasonable life, according to the development goals set by the UN. So we have to tend to look at technologies, not technology. There's not one solution that would do the job. Solar energy, yes. Wind and wave energy, yes, but I mean, even though it's for a long time was something you say, you shouldn't say that, nuclear energy is maybe, at least in a transition period, something that we should look into. Then there are other ways of looking at it also, because you may also have to take the greenhouse gases out of the atmosphere. There are technological ways of getting the greenhouse gases out to deposit them. But there you have to be very careful, because some of these techniques have undesired side effects, because it may cost energy to take, for example, CO2, carbon dioxide, out of the atmosphere, and then you end up even polluting more than you take out of the atmosphere. If you use natural processes such as algae in the ocean to let them eat up the carbon dioxide, then you can bind the carbon within these plants, but they may pollute the oceans, which may have a profound effect on the ecosystem of the oceans. So there are never simple solutions. If there had been simple solutions, they probably would have been employed by now. Then there are some solutions that you could consider as quick fixes maybe, and they initially seem very, very nice, but the good advice is not to go there. It's called geoengineering. And it has the idea that you do various effects on the entire planet, the entire climate system. This is the volcano Mount Pinatubo that exploded in the Philippines in June 1991. Enormous amounts of dust and gas were thrown into the atmosphere, and especially enormous amounts of sulfur dioxide. Here you can see a satellite image of the sulfur dioxide cloud spanning the entire planet. It was there for a very, very long time until it dissipated. And sulfur dioxide, it acts as a mirror, so it reflects sunlight that's coming in. So the average temperature of the planet, it dropped over a 15-month period with 0.6 degrees Celsius. 0.6 degrees. It then, of course, rose back up again. And then people have suggested, even Nobel laureates have suggested, let's just pour some sulfur into the atmosphere. It will work as a mirror. Yeah, but we've been spending quite a long time trying to get sulfur out of the atmosphere because it causes acid rain. So again, it's not a simple solution. And even more science fiction-like, the English, US-based astrophysicist Roger Angel, he at some point suggested that we would put a swarm of small lenses or mirrors in a point between the sun and the earth, so we could regulate the amount of sunlight that was falling on Earth. And you say, okay, we can just turn the temperature a little bit up if we need that, and turn a little bit down if we don't. First of all, you are only dealing with symptoms here, and you're not dealing with the core problem. Secondly, such a system here, who should have the keys to it? Who should decide whether we want it warmer or colder? I mean, building a weather machine is probably not a very good idea, because there are people who want sunlight and people who want rain, people who want wind and people who do not. So we should not, I feel, tamper with the climate system and our planet on that kind of scale. But looking to the sun, not just for the energy that the sun is radiating, the sun has the energy source that we really would like. We would like to have what's called fusion energy. Fusion energy is clean. Fusion energy, it melts atomic nuclei together rather than splitting them as we do is with normal nuclear reactors, so it has no undesired effects, and it will not explode like a nuclear reactor can. So the problem is we do not yet have a technology that can enable fusion energy on Earth. There are various projects, but they have a long time perspective. So here, funding could be a good thing. There are various versions of fusion, and one of them is actually fusion of what's called helium-3, which is a light version of the second lightest natural element called helium, which is coming from the sun, and it's deposited in the surface of the moon. So if we develop the technology of actually doing fusion with helium-3, we could go to the moon, we could get helium-3, take it back to Earth, and could have clean energy for the entire globe. I know this is, you could say, a fantasy, but it's not a completely unfeasible fantasy if we really want to go there. So let me finish, and I'll just finish where I started with rocket science, because this year we are celebrating the 50th anniversary for the first manned lunar landing, Apollo 11, which is here in July. And when you look at the Apollo projects, many people say, whoa, it was very expensive. Yeah, okay, yeah. The Vietnam War was 6 to 7 times more expensive, so it depends on how you prioritize your funding. And people say, it was only politically motivated, which is right. Here you can see the famous image of Buzz Aldrin saluting the American flag. You can just see his fingers because he's saluting the flag. This was the essential need. That's why we actually did the Apollo project. It was to take that one photo. Yes, there were a lot of technological developments that were made. I would argue they would have been made anyway, maybe just a little bit later. Did we get a lot of science out of Apollo? Yes, very, very much, but you really don't sell it on that, unfortunately. So what is the main lesson learned from the Apollo project? From my perspective, and this is where we can couple this to the discussion about green transition. If humans may set themselves a very ambitious goal with a very hard deadline, and most importantly, are willing to pay what it costs, then we can achieve it. So it's all about priorities. It's all about taking the common decision to do it within a deadline, and not just keep talking about it. Oh yeah. This is my final slide, and just to remind ourselves, we only have, at least for now and in the foreseeable future, one place to live. So we better shape up and take very good care of it. It demands that we really use technology in the best possible way. And here it's important to say that science and technology does not in itself solve problems. Decisions how to employ science and technology, on the other hand, do, if we're willing to make strategies which are also funded and followed along and continuously updated in order to optimize what we're actually doing. So it will demand from scientists and everybody that we really keep thinking. And also importantly, it's not all about science and technology. We are human beings. For us, arts and humanities are equally important. And there's an interesting story. It may be an anecdote, but it's definitely an interesting way of seeing things, that during Second World War, it was decided in the United Kingdom to cut support to arts and humanities because of the war effort. And then it's supposedly that the Prime Minister Winston Churchill said, if we do that, then what are we fighting for? And you could argue here that if it's all about technical solutions and not also about the beauty and the reason why we are humans, then there's no reason to struggle at all. It takes that you have an open mind, just not so open that your brain falls out. Thank you for your attention.